Hello, my math friends. This is Mrs. Schlecht. And in this video, we're still going to be working with those algebraic equations, but we're going to be using some fractions, decimals, just like rational numbers. All right, my friends, so you know that there's a few materials you need in order to be successful for this activity. First, you're going to need your Envision book. Remember, we're still in volume 1. Second, you're going to need your math notebook to take those beautiful notes. Third, you're going to need a pencil. And then fourth, last but never, ever, ever least, Mrs. Schlecht's most favoriteest thing, that positive math attitude. All right, my friends, so this video goes really well with lesson 4-5, which is, of course, in your Envision book. The key concepts can be found on page 212. Now, the only difference between this lesson and the previous lessons that we've been working on is the type of numbers that we're working with. So if you remember, we were solving for some unknown values, right? We were using variables and we were trying to figure out what their actual value was, right? Now, in past lessons, we only worked with whole numbers. So we never had a remainder, we never had a decimal, we never had a fraction. We just had these beautiful whole numbers. Our life was so nice and easy, right? But we're going to crank it up a little bit, right? We're going to kind of lift it up to that next big 6th grade step. And instead of just having those nice whole numbers, we're going to deal with some decimals, we're going to deal with some fractions, but don't worry, some whole numbers will still be in there as well. So the first example that we're going to look at together is on page 213, and it's number 6. All right, so for number 6, we have t, that's our variable, that's our unknown, remember, minus 2/3, that equals 25 3/4. So remember, we have this expression over here, and because we have that equal sign, we know that the value of t minus 2/3 is equal or the same. It's equivalent to 25 3/4. All right? Now, remember last week, think back to last week, where we talked about those inverse relationships, right? Those inverse operations, which again just means the opposite. So as we're looking through this expression, I notice, hey, we got a subtraction sign. Now remember, in order to isolate the variable, I want t all by its lonesome. So how do I get t all by itself? Well, I got to do the opposite of subtracting that 2/3. So what's the opposite of subtracting 2/3? Adding 2/3. You're right. But do you remember those properties of equality, my friends? That told us that whatever you do to this expression, you got to do to this expression over here because it has that equal sign, which makes it an equation, which makes it all equal and equivalent to each other. So we're going to add 2/3 to each side of this equation so that we can undo that subtraction and figure out what the value of t is, all right? Remember, if I subtract 2/3 and then I add 2/3, that just cancels each other out. That's just like taking t and just subtracting 0, right? So these two values will cancel each other out, which will leave t all by itself. So again, subtracting 2/3 and then adding 2/3, that cancels each other out. So now I've isolated the variable. I have my variable, which is t, all by itself. And since we know about those properties of equality and balancing equations, we know that if you add 2/3 to one side, you also need to add that same value, 2/3, to this other side, correct? So we can now say that t is equal to 25 3/4 plus 2/3. Now, all we need to do is add two fractions. But notice that these denominators are not the same. So remember, let's think way back. When you are adding or subtracting fractions, you need to make sure that they have the same denominator. That's the number on the bottom so that you can actually add or subtract. Let's take a look at this piece. So let's look at this mixed number and this fraction. We have 3 as a denominator over here. We have 4 as a denominator up here. Now, do you remember those whole common multiples that we talked about a while ago? Well, my friends, this is when that strategy, that concept is really going to help us out. Let's think of our 3 times tables and our 4 times tables. What's the least common multiple? What's the smallest number that these both have in common? It's 12, right? I know that I can do 3 times 4 to get 12 or 4 times 3 to get 12, right? So now what we're going to do is we're going to create equivalent fractions so that they have the same denominator, right? So what I mean by that is I want to know 2/3 is actually how many twelfths, And likewise, 3/4, well, how many twelfths is that? Again, we're not going to be changing the value of these fractions, my friends, right? All the values are going to stay intact, but we're going to change the look of it so that we can actually perform these operations, right? So think to yourself, what do I need to multiply 3 by in order to get 12? And whatever we multiply the 3 by to get 12, you also need to multiply the 2 by that same number to get your numerator. And we know that if we take 3 and we multiply it by 4, that's going to give us 12. So to be fair and to remain, the same value, whatever you do to that denominator, you also need to do to that numerator. So just like 4 times 3 equal 12, now we'll need to do 4 times 2, which equals 8. So what we just discovered, my friends, is that 2/3 is equivalent to 8/12. Now let's check out this mixed number. So a couple things I would like you to notice here. Notice that our whole number, that 25, we're not doing anything to that at all. That's a whole number. That's nice. Just leave it alone, okay? But now let's take a peek at this fraction, 3/4. So same thing. If I'm wanting 12 to be my denominator, I know that I need to take 4 and I multiply it by, we'll multiply that by 3. So 4 times 3, that gave us 12. And 3 times 3, that gives us 9. So what we did, my friends, is that we made these two fractions into fractions with common denominator, that same denominator of 12. And now I can actually add it and figure out what t is. So all I did now on this second line, my friends, is I rewrote our mixed number and our fraction with our new common denominator fractions so that we can actually add those together. So now think to yourself, well, 25 plus nothing is going to be 25. And now we're going to add our fractions. So if I have 9/12 plus 8/12, how many twelfths do I have altogether? That would give us 17/12. But do you notice we now have an improper fraction? Why is it an improper fraction? Because our numerator is larger than our denominator, my friends. So now what I'd like to do is I want to take this improper fraction and let's make it a mixed number. When we take that improper fraction of 17/12 and we make it a mixed number, we know that it's actually equivalent or the same as 1 and 5/12. So now what we need to do is we need to add this whole number with this mixed number, and that will give us the final value of t. Our final answer for number 6, my friends, would be t is equivalent to 26 and 5/12. Friends, so the next one that I'd like to look at together is still on page 213, but now it's number 7. And you'll notice we have f over 2, and that's the same or equivalent as 5/8. Do you remember that fractions just represent division, right? So what this actually means is that we have f, which is our value, which we don't really know right now, right? It's just a variable. And if I divide that amount by 2, then my answer is 5/8. So think to yourself, if I'm dividing by 2, and that's how I get my final answer, well, in order to get f, my variable, all isolated, all by itself, I have to undo that division. And how do you undo division? Well, you use that inverse operation, the opposite operation, which is multiplication. All right, we're going to multiply. So think to yourself, if I divide it by 2, then how am I going to undo that dividing by 2? What do I need to multiply by? Know that in order to undo dividing by 2, we need to multiply by 2. Notice that Mrs. Schlecht didn't just use that old X to show multiplication. Oh no, we're like big time 6th graders, right? So notice that I'm using that dot between 2 and then this fraction and between this fraction and 2, right? But remember, that dot represents multiplication. So now, my friends, remember, if we divide something by 2, but then we multiply it by 2, that's just going to cancel each other out. So we'll get f, our variable, all isolated and alone and all by itself. For this step, my friends, remember, if we multiply by 2 and then divide by 2, that cancels each other out. So we'll get our variable, which is f, all isolated and alone, all by itself. So now I know that f is equivalent to 5/8 times 2. But did you notice, instead of just having 2 as a whole number, I made it into an equivalent fraction. Anytime that you have a whole number, if you add 1 to that denominator, doesn't change the value, it just changes the look. Now, why did I decide to do that? Great question. Here's why. Because when you are multiplying fractions, all you need to do is multiply the numerators multiply the denominators, and then boom, you got your answer. You know that when you're multiplying fractions together, you just multiply the numerators. So in this case, it would be 5 times 2. And then you multiply the denominators. And in this case, it would be 8 times 1. So we know that 2 times 5 is 10. 8 times 1 is 8. But now you have an improper fraction, right? Because you have a larger number on top than you do on the bottom in your denominator. So now can we please convert this to a mixed number? We know that the improper fraction 10/8 is the same as saying 1 and 2/8, or, because we can simplify this, 1 and 1/4. So again, my friends, in number 7, the value of f is either 1 and 2/8 or 1 and 1/4. All right, my math friends. So the next example I'd like to look at together, still on page 213, but now it's number 11. So first, remember, for problem number 6, we used addition to solve. For problem number 7, we used multiplication to solve. Now we're going to be using division to solve, right? Now, how did I know that? Well, because I know that in our original problem, we have 1 and 8/10, and then I'm multiplying it by that variable. It's x right now. I don't really know what the value is. And then I know that the answer, the product of that multiplication expression, is 40 and 1400ths. Now we need the inverse operation, or the opposite operation of multiplication, in order to solve this. And we know that the opposite of multiplication is division. So what am I dividing each side of my equation by? We're going to divide each side by 1 and 8/10. Now notice I wrote it as a fraction, but just like we've talked about in class, just like we talked about with example number 7, this represents division, all right? So even though you might think, oh, why'd you just write a fraction, Mrs. Schlecht? Yes, sort of kind of did, but the intention, the meaning that this actually has right now, my friends, is division. So we know that if you multiply something by 1 and 8/10, and then you divide it by 1 and 8/10, that's going to cancel each other out, so we'll have our variable all by itself. So my friends, we now know that x is equivalent to, or x is equal to, 40 and 1400ths divided by 1 and 8/10. Now notice we have a decimal divided by a decimal, and there are some certain rules that go with that. So let's review this piece. What we did is we took this fraction, which was representing division, and we just put it in the standard old division algorithm that we know and love so much, right? Now, do you remember that we have a decimal in our divisor? We also have a decimal in our dividend. Now, it's okay for a decimal to be in our dividend. That's okay. But you can never, ever, 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 ever have a decimal over here in your divisor. So think to yourself, what I need to do is, instead of 1 and 8/10, I want this to be a whole number. I want this to be 18. So what you need to do is just move your decimal over one spot over here. What you're really doing is you're multiplying by 10, right? So that instead of 1 and 8/10, multiply that by 10, you get 18. But remember, whatever you do to your divisor over here, you also need to make sure that you do to your dividend over here. So if you're scooching your decimal back one spot over here because you're multiplying by 10, then you also need to multiply this by 10, or represent that by moving the decimal over one spot as well. So what are your new numbers that you're using? Now we have 18. That decimal is gone because we multiplied by 10. It's out of here. But since we had to make sure we keep the same value, right, we need to also multiply our dividend by 10 as well. So now we have 401 and 4/10. So now, my friends, I can actually do this division, right? Because I have no decimal over here, a decimal over here, that's fine, right? So remember, whenever you are dividing with a decimal, that decimal just first comes straight up. Now I can think to myself, well, can 18 go into 4? No. Can 18 go into 40? Yes, it totally can. How many times? It can go in there 2 times. So notice I put the 2 directly over the 0 because, my friends, we were trying to see how many times 18 could go into 40. Not 4, not 401, 40. So that 2 goes right above that 0. Place value matters, people. Place value matters. All right, so now think to yourself, well, 2 times 18 is what? 2 times 18 is 36. That means that now I'm going to take 40 and I'm subtracting 36. So we know that 40 minus 36 is 4, but wait, there's more. We now need to bring down this number 1. Again, how many times can 18 go into 41? It can go in there twice. Nice job. And notice that that 2 is written directly above that 1 on this side of the decimal because we were still dividing with those whole numbers, right? So now again, what's 2 times 18? We know that 2 times 18 is still 36. So now we're going to take 41 and we are subtracting 36, which would give us 5 as an answer. But wait, there's more. Now we need to bring down this 4 to make 54. But now, since we are behind the decimal, since I brought that value down that was behind the decimal, whatever this answer is, we're now behind the decimal, right? Again, place value matters, people. It's a thing. So now think to yourself, well, how many times can 18 go into 54? It can go into 54 3 times. Notice that I wrote the 3 behind the decimal because we had used this 4, which was also behind the decimal, to make that 54 to begin with, right? So now what's 3 times 18? 3 times 18 is, in fact, 54, and we know that 54 minus 54 is 0. So what does that mean into the context of like our regular problem? Our original problem, remember that we had 1 8/10 multiplied by x. To undo that multiplication, we needed to divide it by 1 8/10. And then we knew that x was the same or equivalent as 40 and 1400ths divided by 1 8/10. And after we did our division in that beautiful standard algorithm, we discovered that the quotient or the answer to that division problem was 22 3/10, which was the value of x. My friends, so the next problem that I'd like to look at together, still on page 213, but now this is number 12. Remember, in that first problem, number 6 that we did together, we used addition to solve. In that second problem we did, number 7 together, we used multiplication to solve. In that last problem we just looked at together, number 11, we used division to solve. And now, last but not least, we're going to use subtraction to solve this one. 12, we have 17 3/10. We're adding some mystery number, our variable v, don't really know what that is yet, and that gives us a sum or an answer of 22 3200ths. Now remember, if we are adding something, we need to do the inverse operation or the opposite operation. How do you undo adding? In order to undo adding, we need to subtract, right? So what I will be doing is subtracting 17 3/10 from each side of my equation because I want to keep it balanced, right? I want to keep that same value throughout so that I actually know what the true value of v is, right? Remember, if I add something and then I subtract something, that's just going to cancel it out. Now I have my variable all isolated all by itself, right? So now I know v is equal or the same as 22 3200ths minus 17 3/10. Now, my friends, a couple of things to keep in mind when either you're adding or subtracting decimals. Place value matters, right? Take the time to line up your problem so that you know which numbers you're adding and subtracting together. This is what I mean. Notice here, my tens place are lined up, my ones places are lined up, my decimals are lined up, my tenths are lined up. If I had more numbers behind my decimals, then those would all fall into place, right? I know this might seem like a simple step, but believe me, taking the time to actually set up your problem correctly is going to make your life so much easier, all right? So now let's look at this. What's 2 minus nothing? 2. Now what's 3 minus 3? 0. But now we need to look at this decimal. Remember, decimal just comes straight down. But my answer is going to have 200ths as part of the answer, but I still need to do this whole number piece, right? Now, perhaps you know what 22 minus 17 is, and you can just write an answer down there. That's awesome. Maybe you're not so fast, and that's okay too. Think to yourself, well, 2 minus 7, I can't really do that, so I need to borrow. Where are you borrowing from? Your 2 10s. So instead of having 2 10s, you're going to have 1 10, And then you'll carry that little extra 10 over to the 2 over here. So instead of having only 2 ones, you'll have 12 ones. Now 12 minus 7 is 5, and then 1 minus 1 is 0. So our final answer for number 12 is B is equal to 5 2/100. Right, my friends, so that was just a quick run through over lesson 4-5, which still has us working with those algebraic equations and solving for some unknown variables. But now we're having lots of fun with whole numbers and mixed numbers and fractions and decimals. As always, if you have any other questions, please let me know.